Let me go ahead and start. These notes are online. Actually, before I start, I just wanted to point out there is homework on WebAssign that will be due. I think I said it due Friday, so you have up until the exam to get it done. There's also 2 study guides posted. Y'all don't have to do those. There's also another study guide posted on Blackboard. So you have 3 study guides in all, 1 homework, and that was all I had to say on that. So having said that, let's get into it. In the week 7 notes, we're going to go over section 3.6 to 3.8, starting with 3.6. So before we really get into things, I want to bring up a particular structure that sometimes shows up in functions. It's called an asymptote. What an asymptote is a value that your function can approach in some way. So we can have 2 different types of asymptotes that, generally speaking, you have vertical or horizontal asymptotes. And one of the first ways we will learn to evaluate asymptotes is to apply the limit. There's going to be 2 limits in particular that we're going to be concerned with. The limit from the left to the right as we approach some value c, and then a limit as we approach infinity, plus or minus. So having said that, let's check out the definition of a vertical asymptote. A vertical asymptote, like I said, or like I started to kind of hint at, is evaluated by taking the limit as x approaches to some c value from the left or the right. If in that event, so let me write this on the board. So if we have the limit as x approaches c from the left, and f of x comes out to be plus infinity or minus infinity, I'll put those in parentheses for now. I'm actually going to do the same thing, the c. So if we approach the c value either from the left or from the right, and our limit comes out to be infinity, then that means that c value represents a vertical asymptote. And we say that there's an asymptote whenever x is equal to c. So as an example of this, let's consider the limit as x approaches 0 from the left of 1 over x, and the limit as x approaches 0 from the right of 1 over x. For both of these, we get 2 different infinities, right? Negative infinity and positive infinity. That's why we say the limit doesn't exist. But notice, as we approach 0 from the left and from the right, we approach a negative infinity and an infinity, which implies then, or directly tells us rather, that when x is equal to 0, we have a vertical asymptote. And we can see that in the graph of this. When we consider the fact that intuitively we understand that the graph of our function will never cross the line x equal to 0, right? Make sense? Cool. So as a bunch of different examples of different asymptotes, notice in A, as we approach 1 from the left and from the right, we're going to get to negative infinity and infinity. In B, same thing, C and D. These are just different examples of what an asymptote might look like graphically. as well as how we would find it algebraically. Or rather, how we would find it using the limit. So as an example, let's consider this function x plus 2 divided by x squared minus 2x. Now, we're only going to have discontinuities whenever our denominator is equal to 0, right? So why don't we just isolate our denominator, set it equal to 0? When we do that, we find that x is either equal to 0 or it's equal to 2. So these are going to be the points we're going to want to test with our limit, right? When we do, we find that we have an asymptote at both values. Now remember, we have to test this with our limits. And I think this next example will show why. So we've got this function. Let me erase this. We've got this function, f of x is equal to x squared plus 2x minus 8 divided by x squared minus 4. Now, looking at this, it may not be obvious right away, but we're going to have a discontinuity of two different sorts. We're going to have an asymptote, so a jump discontinuity, right? We're also going to have a discontinuity where there's just a hole in our function. We're going to have to plug it somehow. Now, the reason why these two things show up is because of what's happening under the hood. Let's factor out x squared plus 2x minus 8. When we do, we're going to get x plus 2, or my mistake, x plus 4, x minus 2. And now let's factor out our denominator. This thing's going to come out to be x plus 2, x minus 2. Well, hey, these things can cancel, right? So what we get is that our function is equal to x plus 2 over, x plus 4 over x plus 2 whenever x is not equal to 2. Now, why is that? That happens because if we look at our denominator before we try to simplify things, our denominator can't take on 2 and negative 2. Agreed? So x can't be plus or minus 2. Well, x still can't be minus 2 down here. But it could be 2 in this case. So we have to make the statement that x can't be 2. Does that make sense what I mean? In order for these things to be equivalent, we're going to have to keep that discontinuity somehow. Now looking at it, check it out. We've got an asymptote at negative 2, and when x is equal to 2, our function's undefined. That's that jump, or that discontinuity I was talking about. So from this, we can say, all right, cool. Now all I have to do, just from the algebra we've done thus far, to check this, I only need to take the limit as x approaches negative 2 from the left and from the right. Of x plus 4 over x plus 2. And this thing is either going to give me plus infinity or minus infinity, right? So just a note, this is not proper notation that I've written down here, right? Like we can't just compress everything. But for the sake of room, I'm writing it that way so that we understand we're taking the limit as x approaches -2 from the left, and then we're taking it again from the right. And we're getting plus infinity and minus infinity accordingly. Yeah. So checking out the work now, they did the exact same thing. They factored out the numerator and the denominator. They said, hey, we can drop this term, or this factor of x minus 2, rather. We can drop that out. But when we do, we have to note that x can't be equal to 2 now. So with that, now we're just going to apply our limit. Does this make sense? Yeah. All right, so new type of limit, a limit at infinity. What we're going to say here is that a limit at infinity is either the limit as x approaches infinity of f of x, or the limit as x approaches negative infinity of f of x. But we really can't just say a limit as x approaches infinity or as x approaches negative infinity, because we can't approach it from both sides, right? Like there's no way to approach infinity from the right. We can only approach it from the left. Similarly, we can't approach negative infinity from the right or from the left, so we have to approach it from the right. So there's a little bit of trickery in the notation here, but generally we write it this way just because it's understood. Why bother with that plus or minus on the right? Cool with this? Now, let's consider a case. Let's consider the case when when our function is equal to 1 over x. Now we know that the graph of 1 over x looks something like this. So when x approaches infinity, it's going to approach 0, right? Our function is going to approach 0. And when x approaches negative infinity, again, our function approaches 0. Same idea, we're just looking at the tendency as we go on to forever. In this case, we would say that 0, y equal to 0, is a horizontal asymptote. I hope I'm spelling that correctly. Asymptote? Yes. Oh, no, I forgot the M. There's an M in there. Now, as two different examples of types of asymptotes, horizontal asymptotes we might have, we've seen this first case where we have the same asymptote. But we could have a case where there's only an asymptote as we approach infinity. Or we could have a case where there's only an asymptote as we approach negative infinity, or that they have different asymptotes. Is everybody cool with this? Or we may just not have an asymptote at all. So we have to check both cases, as x approaches infinity and as x approaches negative infinity. So just checking out a quick example. We've got the limit as x approaches infinity of 5 minus 2 over x squared. Well, the limit of a constant is a constant, right? And the limit of 2 times a function is just 2 times the limit of that function, right? So we can move down to here and we can say, hey, the limit of 1 over x squared as x approaches infinity, we know that to be 0. So this comes out to be 5 minus 0, or just 5. So our asymptote as x approaches infinity is at 5. Now, in this case, because of the symmetry of x squared, we have the same asymptote in both directions. And that's why they just went ahead and skipped it. But we would normally have to check both cases. So, having said that, there's a couple quick rules behind how asymptotes, horizontal asymptotes, of rational functions are going to behave. In particular, we have if our function f of x is equal to p of x over q of x. In case 1, the degree of p of x is less than or larger than, is less than, yeah. Then the degree of q of x then the limit as x approaches plus or minus infinity is equal to 0. Then we have the second case where degree of p of x is greater than the degree of q of x. The limit of x going to plus or minus infinity is going to be equal to the coefficient, the leading coefficient of p divided by the leading coefficient of q. And then finally, we have the case where
Did you mean equals to? not greater than on the,
Oh, you're right, I did mean to say equal to, thank you. I'm thinking about the next one at the same time, like, where am I going? You're right, yes, thank you. And then in the case of the greater than, there is no horizontal asymptotes. Does this make sense to everybody? Thank you for catching that. So having said that, we've got three different cases here that we're going to be presented with. We've got the case where Q has a degree higher, Q is the same degree, Q is one less degree. So applying then these rules, a quotient has a higher degree. So we are in that first case, right? Our quotient in the second has the same degree. So we're in that second case and then plan over that third case. To compare these graphs, check it out. This thing is going to go to 0. This thing's going to drop to 0 and then come back up to 0. This is going to have a limit at -2/3, which is what we're seeing here. And then the final case has no horizontal asymptote. Instead, it has a sort of diagonal asymptote that I don't think we talk about in this class. Is everybody cool with this? No? Folks at home, what do y'all think?
Good.
Yeah? No. All right, cool. All right, in that case, I'm gonna let y'all try this problem really quick. For those of y'all at home who can't see which slide we're on, it is slide 19 of week 7 notes. So we're going to skip over the second part as I do it on the board, because we're going to see it when I flip to it in a second. Instead, I'm going to ask the question really quick. What happens as x goes to infinity of our average function? What is that going to approach? What do y'all think?
.5.
Yeah, exactly. Because what's gonna happen is this thing's gonna go to zero, right? This term, 5,000 divided by X, has to go to zero. And all we're gonna be left with is this 0.5 term. So yeah, this has to go to 1/2. Now, answering these other questions, as the book gave it to us. In the case of 1,000, well, 5,000 divided by 1,000 is 5, plus 50 cents, we're gonna get 5.50. In the case of 10,000, we're gonna get $1. In the case of 100,000, we're gonna get 55 cents. So notice what's happening is these things are decreasing, right? The cost per item is decreasing. Decreasing to 50 cents. So this is kind of, looking at it this way, it's kind of like that tabular view that we took of the limit at the beginning of the semester, right? And all we're saying by looking at each of these three cases, we are getting closer and closer and closer to 50 cents. Whose only good album was In the Club. Anybody at home who did not get that joke, please go back to daycare.
That was a good one. That was a good one.
Nonetheless, though, looking at this, like I said, as X goes to infinity, we're gonna find out that one term goes to zero and all we're left with is the 50 cents. Okay. What about this case? I actually hate this problem because it suggests something that I don't think is a good thing to suggest in class. It's misleading in a lot of ways, but whatever. Politics, my personal politics aside of this problem, what we've got is a manufacturing company that's trying to figure out what the cost is going to be for removing pollutants from its smokestacks, right? And what we've got is a function of cost of the cost function as a function of the percentage of pollutants being removed. And looking at this, we're trying to figure out if we have a vertical asymptote or a horizontal asymptote first and foremost. And then trying to find out what the vertical asymptote of this function is going to be. Having said that, looking at this function and just testing a few values close to 100%. We find that this function is a vertical asymptote at 100%. In other words, the cost of removing 100% of the pollutants from whatever it's putting out into the atmosphere is going to be infinite, is what this is suggesting. Like I said, I have political qualms with this particular problem because, you know, science and all, but that's a thing. Anyhow, jumping to the next section, 3.7. For those of y'all who might want to review, I would strongly suggest checking out these sections because we're about to put all of this back together. So if any of these things are a little rocky to you, go back to one of these sections and review it. Shoot me an email, come to my office hours, whatever. Just do whatever it takes to understand this material so that we can understand what's coming up. What we're going to be doing today with all of this stuff is going to be trying to find the graph of a function without actually going through and finding point values for different x's of our function, right? So instead of having to go through and say, all right, what is our function at x equal to 1? What is our function at x equal to 2, 3, 4, 5? We're going to skip that and instead use mathematical logic to figure out what this graph is going to look like. So to start off with, let's imagine we've got the function x cubed plus 3x squared minus 9x plus 5. We want to graph this thing. Looking at it, do you think you know what it's going to graph into? If I told you it was a sideways S looking thing, would you have guessed that? The way we go about factoring or graphing these using that sort of logic approach. So we start off by saying, all right, what are our intercepts, our x and y intercepts, first and foremost? That's what we're trying to do up here. Then we say, all right, now what's our derivative going to be, and what are our critical numbers? Once we get our critical numbers, we're going to take the second derivative, factor it, and try to set that equal to 0 and find out what those values, what those x values are. And then we set up a table with all the information enclosed. So to start off with, we know that when x was equal to -3, we have a relative max because our first derivative is equal to 0. When x is equal to 1, we have a relative min, again, because of the 0 and our derivative test. And we just run through the logic this way. Does this make sense, what I mean? So once we get these points, and this is a little bit of information, we can now sit down and say, all right, cool. Let's start sketching out what our graph looks like. Show what I mean. We know our graph is going to be, or our function is going to be equal to 0 whenever x is equal to 1 and -5. Because that's our x-intercept, right? Said 1, not 0. So 1. Let's say -5 is over here. Now, from here, our second derivative tells us we have critical values at 1 and at -3. So let's go ahead and mark -3. We know something is going to happen around there. Finally, when x is equal to -1, our second derivative is equal to 0. Something's going to happen here too. have all these colors, but I don't have white. All right, now, we know on the interval from negative infinity to -3, we're concave down, right? So it's going to be something like that. But we're increasing. Let me start there, actually. Using the first derivative test, we're increasing on that interval. Now, between -3 and -1, we're decreasing. From -1 to 1, we're decreasing. And from 1 to infinity, we're increasing. Now this told us that at -1, we have a point of inflection. Right? And before we go any further than that, I want to point out, we already know something about our graph because since we're going through x equal to -5 and y equal to 0, since we have to touch at least this point, and we know we're increasing, we now know that our function is going to have to go through that point, right? I wish I had a different color I could work with. I guess I could go with purple. Let's do that. We know we're going to have to go through that. We know that we're going to have to dip down at -3, and we know we're going to have an inflection point at -1. And we know that we're concave up from -1 to 1, concave down from -1 to -infinity, right? So all of this together tells us, going through this point, we have a relative max at -3. We found that out from the first derivative test. So we must be decreasing now, going back down. But we hit an inflection point when x is equal to -1, so our concavity changes. And we start to increase again when x is equal to 1 because that was one of our critical numbers, right? So our function has to look something like this. Folks at home, how well can you see that?
I can see it well.
It's clear.
I'm sorry, I have no clue what y'all just said.
We can see it well.
Awesome. All right. So now comparing this then with what we've got, Okay, so my drawing's not the best, but pretty much the exact same graph, right? Like, we go up to our relative max, we go down to our relative min, we keep that sort of S shape, right? That sideways S. Pretty much the exact same graph. Like I said, it's not quite as elegantly drawn. So having said that, as another example, x to the 4th. Now, x to the 4th, I'm going to go ahead and jump to. It's going to come out looking like this. We're going to have an intersection at 0, 0. We're going to have another intersection at 4, 0. We're going to have a relative min at 1, negative 27. A point of inflection at 2, negative 16. So looking for those points in here, when x is equal to 1, our function is equal to negative 27. We said that was a relative min. We at least know it's a critical number. So we know something's going to happen there. So on our graph, as we're drawing it, we would mark kind of like what I was doing before. We know we have another critical value at x equal to 4. But in this case, it's an inflection point. So let me draw this out instead of explain it. All right, starting off with, we have an intercept at x equal to 0 and at x equal to 4. X equal to 0, x equal to 4. We have critical numbers at 1 and x equal to 4. At 1 and x equal to 4. We have an inflection point, or rather we have second derivative equal to 0, I should say, when x is equal to 2 and x is equal to 4. So x is equal to 2. Now, breaking this up from negative infinity to 1, from 1 to 2, from 2 to 4, and 4 to infinity. In this first interval, we're decreasing. In this second interval, we're increasing. Third interval, we're still increasing. Fourth interval, we're still increasing. All right. So we're decreasing on the interval negative infinity to 1. So we know we're going to have to go through the origin. Something like this. Right? Because we're decreasing through this interval, and we know we have to touch the origin. It's an intercept, right? Now, looking at this, we go from decreasing to increasing with a critical number at 1. So we know it has to be a relative min. First derivative test, right? So at 1, our function is going to have to do something like this. At 2, we have no critical point, but we have a second derivative that's equal to 0. So it's got to be a point of inflection. Notice we're going to be concave up from negative infinity to 2. So going to 2, it have to look something like that all the way through it, right? On 2 to 4, we're concave down. And on 4 to infinity, concave up. So we're going to have to look something like a wavy type motion moving through it, right? Okay. Now, we also know we're going to have to go through this point 4, right? We know it's an inflection point. We know it's an intercept. And it's a critical number. So at this point, we have to do something like this. Agreed? We're increasing through these 2 intervals. So we know we're going to do something like this now. And we're decreasing from negative infinity to 1. So we know the rest of it's going to look something like this. And what was it that happened at 2? Oh, it's a point of inflection. So 2 should be drawn more like this. Now comparing this with our graph, looks pretty similar actually. I mean, barring my atrocious ability to draw, looks pretty similar, right? Okay, maybe not quite as good through there, but this is going to be the method that we want to use going through and drawing out what these graphs look like. Notice this is a lot shorter actually than if we were to go through and find a bunch of points. Like how many points would it take to actually draw out that graph? I don't know about y'all, but I feel like it would be disclosure. If there's a kid around, hide them a fuck ton, right? Like it's going to take a lot of points. This just saves you time. Now, when are you going to use it? In your workplace? I'm going to be perfectly honest with y'all. This you probably won't use because your computers will do this for you. What this is teaching you is logical mathematical thinking. The point of these problems aren't to teach you some technique that you're going to use this tomorrow, right? Or in the workplace. Unless there's an apocalypse and the internet goes down, you don't need it. But you do need to be able to infer things from data. And that's what this is teaching you here. This right now is not about the math. This is about mathematical thinking. Given very limited information, what can I pull out? How can I address the problem? How can I attack it and tackle it? We're given the function. We have these tools called derivatives. We can use these tools to find out particular things. And we can put those particular things back together to make an inference. So I just want to clarify, this part of the class is not about a tool you're going to use in the sense of needing to graph. It's about the thinking. So for everyone who's like, but when am I going to use it? You're not. You're going to learn how to think. That's what this is. Having said that, another awesome function. So the first thing to notice with this function, you can pull out an x to the 4/3. So factor that out right away. When you factor that out, it's going to let you find where your intercepts are. Automatically, because of the factoring out, you know one intercept's going to be at 0, 0. The other intercept, you're going to have to find by working with that second factor, right? And working through it, you find your other intercept is at 125/8. I don't know about y'all, but I would have never known that just looking at this function. Next, you want to take the first derivative. The first derivative is going to look like a mess, but you can factor out a 10/3 x to the 1/3. When you do, you're going to immediately see that this factor here tells me that I'm going to have a critical number at my origin. And this one, it's going to tell me I have another critical number at 8. Then you're going to go through, take the second derivative, factor it out if you can. When you factor it out, you're going to say, all right, I've got a discontinuity immediately whenever x is equal to 0. So that earlier critical number at 0, it's going to have to be an inflection point at best, right? But you also have this other value, this other 0 that's going to occur whenever x is equal to 1. And now, putting it all together, I'm going to produce this table. I'm going to say, all right, got my first interval I need to worry about from -∞ to 0. I found one of these critical numbers was x equal to 0. X in the interval 0 to 1, x equal to 1, so forth and so on. We're going to break it up based on our critical numbers and our inflection points and our intercepts, right? And we're going to say, what was our function at these hard values, x equal to 0, x equal to 1, x equal to 8. I know I can go ahead and pin those down right away. Because my function is 0 at 0, because my derivative at 0 is 0, and my second derivative at 0 is undefined, and I go from increasing to decreasing, I know x equal to 0 is going to have to be a relative max. I have an inflection point when x is equal to 1, so forth and so on. These are our derivative tests. Then we put it all together to find our graph looks something like this. Notice all of our points that we were concerned with are up here, right? X equal to 0, x equal to 1, x equal to 8. And then our other intercept whenever x was equal to 125 over 8. So another method of going through these would be to start off with each of these point values that you're given. You knew your function had to go through the point 0, 0, and you knew your function had to go through the point 125 over 8 at 0, right? And then you said, all right, well, I knew I was going to have a relative min at 8. I might as well go ahead and find out what that value is, what that functional value is. And then you knew you were going to have an inflection point. So these points of inflections and these critical numbers, they hint at points that you're going to want to put back through your function to find out what your function value is. That's another way of going about it. Because then you can say, all right, I know I have to go through this. I know I have to go through that. I know I have to go through this. I know I have to go through that. What does all of this look like? So to show you what I mean, actually, I'm going to steal some of these points directly off the graph. All right, now, the reason why I wanted to put these down first was so I could line them up with what we have through our solutions. This point 0, 0 came from initially one of our intercepts. Right? We had an intercept at 0, 0 and an intercept at 125 over 8. Then we had critical numbers at x equal to 0 and x equal to a. Let's go ahead and put them through our function and find out what our function evaluates at. Well, x equal to 0 already showed up as one of our intercepts. X equal to a, however, evaluates negative 16. Taking the second derivative, setting it equal to 0, we have another x equal to 0. But now x equal to 1 shows up. So let's go back to our original function, evaluate it at 1. We find out it comes out to be negative 3. Now, using our derivative test, 0 was a relative max. So we were increasing on the left, decreasing on the right. Negative 3 was a point of inflection, but we kept decreasing. So it had to be a particular point of deflection, of inflection, I mean. We went from concave up to concave down, so it had to be that sort of S shape point of inflection, right? We knew from our first derivative test that we went from decreasing to increasing around the 0.8, so that had to be a relative min. Right? Now putting all of this together, we can infer our graph has to do something like this. Right? Going back to the original graph. It's a little sharper in here. This isn't 110%, right? Like, this is a qualitative analysis of what your graph is going to look like. But it's a pretty decent qualitative analysis. Notice it was a lot easier too, having already put those points on the board. So as a pro tip, something I would suggest doing is actually calculating what those points are. So every time you have a critical point or a point of possible inflection, go back to your original function, put that x value through, and then plot that point. Having said that, just a quick summary of what different types of polynomials come out looking like. Anytime you have a polynomial of degree 2, it's going to be a parabola. Degree 3, it's going to come out looking like one of those sideways S's. Degree 1, straight line. Degree 0, straight line. Anything more than that, you start having questions. It can start coming out to be weird things. Having said that, concept check on slide 37. Check it out. Now we're going to get into differentials. A differential is really an approximation tool. And let's go back and think about what all of this means. When we have the derivative, we say that the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. This thing is equal to dy dx or just f prime, right? So for really small delta x values then, if delta x is small, then f of x plus delta x minus f of x over delta x is approximately equal to dy dx or f prime of x. So when we start talking about differentials, differential is really just the dy or the dx. Differential of x is going to be the dx. Differential of y is going to be the dy. What we're really saying is that dy is like the derivative of our function times a small change in x, or infinitesimal in particular. Because what dy dx represent are infinitesimal changes within our function. An infinitesimal being a number smaller than every other number, but close to zero. Right? Makes sense what I mean? So in that way, if I multiply my derivative by dx, I get dy, right? But that's kind of like multiplying my derivative by delta x. So what this dy is kind of measuring, it's kind of measuring the small change in my y values. And what this dx is kind of measuring is a small change in my x values. So our derivative times dx is the same as the small change in y. Does this make sense? Yep. In that way, I did make a good point that I should have written up here. Delta y, delta x, kind of like dy dx is like x. Okay. So looking at the tangent line to our function at a point x. The small change in x can be thought of as dx. And the small change in y can be thought of as dy or delta y. Delta y would be x plus delta x and that functional value, right? But dy is going to give you something a little bit smaller than that. The reason why is because delta x is actually larger than dx. What I'm trying to say here is that what this sort of an analysis allows us to do is approximate small changes in our function. So let's imagine we're given the function f of x is equal to x squared. We know the derivative of that thing is going to be 2x, right? F prime of x is equal to 2x. We want to find the value of dy when x is equal to 1, and dx is going to be 0.01. Let me actually write it slightly different. dy is equal to f prime of x times dx. X is equal to 1. Dx, we're saying, can be approximated as 0.01. So that means then we're going to have 2 evaluated at 1 times the the value 0.01 This is obviously going to come out to be 0.02. So dy is equal to 0.02. Now, comparing this then with delta y, delta y is equal to f of x plus delta x minus f of x. So delta y at x equal to 1, delta x equal to 0.01 is going to come out to be 1.01 squared minus 1 squared I have no clue what this evaluates out to be. So I'm going to skip to what that solution comes out to be is 0.0201. Cool. All right. So notice that dy is a little bit smaller than delta y. Why is that? What's happening here? What do you all think is happening here? One, what have I done here? Let me start there. What's going on in this case? What do you all think? What we're doing is we're evaluating the way error changes. We look at this graphically. Setting delta x and dx equal to 0.01. The way dy changes is slightly different, slightly higher, larger than the way delta y changes. I meant to say smaller than delta y. And the reason why is because dy gives us a good approximation, really close to our x value. But not further away. Does this kind of make some sense? So another way to say what I'm trying to say would be, trying to think of another good example of showing, I know, okay. Later in my notes, error propagation. All right. So one way of thinking about this is delta y versus dy are measuring errors in orders of magnitude of the original measurements. Damn, how do I want to say this? I'm trying to think of how best to state what I'm trying to state. Imagine in this case, we've got a ball bearing. We're trying to measure it, right? The ball bearing is of radius 0.7 inches. And we're told that our measurement is correct up to 0.01 inches. So we've got a caliper, we're measuring this thing. This measuring caliper is good up to 0.01 inches. We know the volume of the sphere is equal to 4/3 pi r cubed. So the change in volume for small changes in r is close to 4 pi r squared times the small change in our r. So the error possible in our measurement, if dr is equal to 0.01, is going to be on the order of 0.0616 cubic inches plus or minus. So what this dr is for small changes of our x value, our x quantity. What's likely to change in our dr value? Does this make sense? Whereas without the limit, we're going to get a worse approximation. And that's the point of this, is to show that the accuracy of error measurement using differentials compared to delta x, delta y, differentials are much better, especially really close to your values. Delta x, delta y, not so great. Having said that, I will let y'all go. If y'all have any questions, I'm going to stick around.